Alrighty, now on to Hess's law. If you think back to the gas law chapter, we talked about Dalton's law of partial pressure, which was one of those things that it seemed odd that we needed to even have a law for it. It was simply that the pressure of a mixture of gases is just equal to the partial pressure of each gas added together. So basically 2 plus 2 is 4. Hess's law is another one of those kinds of laws. Hess's law just states that if a reaction is carried out in a series of steps, the enthalpy change for the overall reaction is the same as if you just added up the enthalpy changes for each of the individual steps. So 2 plus 2 is 4. Now, if only the problems were that easy. The concept's simple. Okay, so here, for example, this energy diagram is showing methane being burnt completely in one step. Methane going from CH4 to carbon dioxide and water. And 890 kilojoules is released when that happens per mole of methane. But you've heard of incomplete combustion, probably. This reaction can actually happen in 2 steps. You can take the methane and combust it only partially to carbon monoxide. That'll release 607 kilojoules. And then when you combust it the rest of the way, all the way to CO2, then that'll release another 283 kilojoules. If you add up 607 and 283, you get 890. Okay, so Hess's law just states that if a reaction is carried out in a series of steps, the enthalpy of the overall reaction will be equal to the sum of the enthalpy changes for the individual steps. All right, here's another one. Okay, here we have the combustion of propane to CO2 and water. Oh no, lost my image, hold on. All right, here we have the combustion of propane, and this is the overall reaction, and here it is in broken down into some separate steps. Okay, here we have methane just being decomposed into carbon and hydrogen. The carbon formed here would be graphite. It'd be nice if it was diamond, but no. Then we have the graphite combusting or synthesizing with oxygen to make CO2, and then we have the hydrogen combining with oxygen to make water. Because honestly, when this happens, when propane reacts with oxygen and turns into CO2 and water, all these little baby steps happen in reality. First, the propane has to get broken up into its individual elements, and then those elements can combine with the oxygen to make our products. So, this is actually 3 steps are going on here. Now, this enthalpy diagram really looks crazy, but just follow along with me here. Where are the reactants? There they are. Okay, so here's our methane and our oxygen. And then here's our products at the very end of it. Now, all the dotted line stuff shows us the 3 baby steps, the 3 little steps that actually are going on here. So first, we have to put in 103 kilojoules in order to decompose the methane into graphite and hydrogen. Then, when we form the CO2 from the graphite and the oxygen, that releases 1181 kilojoules. And then, when we form the water from the hydrogen and oxygen, that releases another 1143 kilojoules. So if you put all that together, 103 going in endothermically to decompose the propane, then the 1181 being released for the formation of the CO2, and then 1143 being released for the formation of the water. Okay, if you add all that together in your calculator, you will get negative 2,220 kilojoules. Okay, so the overall reaction, if it happens in a series of steps, which it actually does, and you add those baby steps together, you get the enthalpy of the overall reaction. All right, so if you look at this, you can see that everything cancels out except for your overall reactants and products. Notice we have a mole of propane in our baby steps, and we have one in our overall reaction. Notice we have 3 carbons, 3 graphites here on the left as a reactant, and we also have 3 carbons over here on the right as a product. So those carbons cancel. Meow, I hear you. Then notice we have 4 hydrogens on the left, and we also have 4 hydrogens on the right, so those cancel. And then notice we have 3 oxygens here and 2 oxygens here on the left, so we add those together, and there's our 5 oxygens. And then all that's left is our 2 products, the 3 CO2s and the 4 waters. This is what you're going to be doing in problems. You're going to be given a series of baby steps and their enthalpies, and you're going to be given an overall reaction and asked to figure out its enthalpy by combining the baby steps. So all of this is going to be given to you. You just have to combine it correctly. All right, so here's another example. This is the one we saw earlier. This is the combustion of methane. The overall reaction for the combustion of methane releases 890 kilojoules, but if we go through an intermediate, incomplete combustion where carbon monoxide forms, and then finish it out and completely combust it, the CO2 and water, we add those enthalpies together and we get the same as if it all would have been done in one step. All right, so basically this comes back to the state function thing. The total change in enthalpy of a reaction is independent of the number of steps. Whether you do it in 1 step or 12 steps, the enthalpy change will be the same. So that is by definition a state function. It doesn't matter how you get there. All right, so enthalpy is independent of the nature of the path. Also, so it does matter when you're dealing with, well, any chemical really, but it pops up with water quite a bit since water likes to be in 3 different states fairly easily. Liquid water and gaseous water are not the same. Okay, gaseous water vapor has a lot more energy than liquid water, so you have to pay attention to the states here. So what I mean is, liquid water and gaseous water, you can't cancel them out with each other. They're not the same. It takes water vapor to cancel out water vapor. Okay, that does make a difference because it takes 88 kilojoules to turn 2 moles of water vapor into 2 moles of liquid water. So we need to pay attention to that. It's mainly just going to happen with water. All right. So the enthalpy is sensitive to the states of the reactants and products. So some tips to remember as you are combining these baby steps to get the overall reaction. The baby steps won't always be given to you in the form you need them to be in order for everything to cancel out and equal the products or the overall reaction. So if you reverse a reaction, the enthalpy is the same, you just got to change the sign. So sometimes you'll have to flip them and reverse them. Also, that enthalpy is tied to the coefficients. So if there's a 2 in front of the water, that's what that enthalpy is related to. So the enthalpy is directly proportional to the amount of the reactants and products in the equation. So let's say maybe in your overall equation you need 4 waters though. So, and you only have 2 in your baby step. It's legal to multiply the baby step by 2 or 3 or 4, whatever you need. But because the enthalpy is tied to those coefficients, if you double all those coefficients, you need to double the enthalpy too. This will all make a lot more sense once we actually do a sample problem. So if the coefficients of a reaction are multiplied by 2, then you need to double the enthalpy. It is an extensive property. Remember, extensive properties depend on the amount of substance present. Intensive doesn't. But since enthalpy is extensive, we got to pay attention to the amount of moles. All right, so since you're going to be combining several reactions, several baby steps, it's helpful to work backwards from the final reaction. All right, so let's look at one here. The enthalpy for the combustion of carbon to carbon dioxide is negative 393 per mole of carbon. And the enthalpy for the combustion of carbon monoxide to carbon dioxide is negative 283. So here it all is written out. Here's your 2 baby steps. Using these data, calculate the enthalpy for the combustion of carbon to carbon monoxide. So we want to combine these together so that everything cancels out except for 1 solid carbon, a half of an oxygen molecule, which I know can't really exist, but that's just how they write thermochemical equations, and 1 carbon monoxide. So, you might have noticed this already. There is no carbon dioxide in our overall reaction, yet it's in both of our baby steps. So we need to cancel this. We somehow need to get rid of it, okay? We do need a carbon, just plain old solid carbon on the left, which we have. We need oxygen on the left, which we have. Don't worry about the numbers yet. First, just make sure you got everything on the right side. Now we want carbon monoxide as a product. We don't have it as a product. It's over here. So we need to flip this reaction and just write it in the other direction. And then when we do that, we need to make this a positive 283. Okay, so here it is flipped. Okay, we've changed the sign, made it 283. We made it so that we're producing the carbon monoxide. So we have our carbon, we have our carbon monoxide. Notice the CO2 on the right is going to be canceled by the CO2 on the left. And now we'll worry about numbers. We have one O2 over here, and we have a half of an O2 molecule over here. So half of an O2 gets canceled out. Okay, it doesn't get completely canceled out because we have a whole and then just a half. So that leaves just a half on the left side. Everything cancels except for what we want in our overall reaction. So now all we need to do is add our baby steps together, and there's the enthalpy of our overall reaction. So it's like a puzzle. These are kind of fun once you get the hang of them. That's the long book explanation for how they did this. This is one of those things that I find it's helpful to, when you're setting it up, write your baby steps and your overall reaction in pen, and then do all your flipping and multiplying and cutting in half and all that and changing your signs and everything. Do that in pencil in case you realize at the end you messed up and you want to start over. Your original information given in the problem is in ink, and so you can just erase real quick and get rid of the changes that you made. Okay, so here's another one. I don't know if I have it. Let me do this one in class with you. It's much easier to show, I guess, live than any slideshow. All right, so ignoring all that, blah, blah. Let's see if I say anything more about Hess's law. Nope, that's it. So that's it for Hess's law. I'll just show you some more on the whiteboard in class, or maybe in a video where I write out the problems using the iPad.